So Alex Rice is here, University of Edinburgh, and the topic here on quantum circuits are just a phase. Um, Former Unitary hack project maintainer, I believe, with your
Yeah,
compiler this past year. So
not
awesome.
for this project, but
Yeah,
yeah.
unrelated, but awesome to have you. And yeah, take it away.
Yeah, so hi everyone. This is some work I've done with with a bunch of collaborators that are on the slide. And so I've already presented this at POPL conference, which is Principles of Programming Languages, but I'm hoping to give a sort of bit slower of a bit slower, more in-depth version of the talk today. And hopefully some of you find it interesting. The sort of overview is this is sort of giving some new high-level primitives for describing quantum computations. So yeah, the overview of the talk is very broadly that I'm going to try and assume very little to nothing. So I'm going to go over sort of this standard quantum circuit model of how I'm sort of viewing these pure quantum computations, um, and sort of describe some of the things that we see as not necessarily the ideal with the circuit model. I'm then going to talk about this new construction that we've added to try and sort of make this more expressive, which is this quantum if-let expression. I'll get, if that means nothing to you at the moment, that's fine. I'm going to get into this, but this is sort of the key primitive that we're adding to our. I should probably say that we're sort of working towards making a quantum programming language here. And then lastly, I'll sort of explain all the rules of that language and give some examples, show some things you can do with it. And yeah, I think I said this before the talk started, but if anyone has questions, just feel free to interrupt or send a chat message or something. I'd prefer people follow along and actually understand what's going on than necessarily getting through all the content. So yeah, and yeah, the I guess this is the minor spoiler of what things are going to look like in this language. But my hope is that by the sort of end of the talk, you'll be able to look at this text and sort of understand what this means. So that's sort of I guess, the spoiler for further along in the talk. So just to sort of set the stage, we're obviously working. Yeah, we're obviously working on trying to model quantum computation, and as we sort of know, this has differences and similarities to classical computation. So whereas in the classical world, our sort of classical piece of data, the classical bit, is either in this false or true state. We have that our qubits are these unit vectors in this complex valued vector space. So we have, in theory, lots more quantum states available to us than in the classical world. So, and this is sort of a strict generalized. Well, it's I guess not a strict general. It sort of generalizes this, at least the data sort of generalizes this classical world in that we can view the false classical bit as this vector here, which I'm going to write like this. So this has a one component in the one component in the sort of first part of this vector space c squared and 0 in the second. And I'm writing this and going to say it as ket 0, which is the sort of standard physics notation for this basis vector. The other classical bit, the true bit, I'm going to write as this ket 1, which has a 1 in the other component of the vector space. So yeah, this sort of allows us to represent these classical values as quantum values. But of course, there's more things we can do on the quantum side. So because this is a vector space, I can sort of take combinations of, I can add these vectors together and scale them. So for example, I can make this ket plus vector, which is adding together the ket 0 and the ket 1, and then normalizing it back to get another unit vector. So remembering that all these sort of qubits are going to be unit vectors. And I can also get this ket minus, which is the same, but I'm going to subtract the ket 1 from the ket 0. And these two vectors will be important later. So it's worth sort of keeping a note of how they're defined. And then the things we're really going to be trying to describe in this talk are these measurement-free quantum computations. So we're really trying to just talk about this sort of fragment of quantum computing where we're not thinking about complex sort of hybrid scenarios. We're really thinking of, we're just trying to run this sort of what's usually called pure quantum computation. And these are modeled by these unitary maps. So yeah, as if we're thinking of like a computation on classical bits, we would usually think of this as sort of some just classical function from our input classical data to output classical data. On the quantum side, we're thinking of, so we started with our input data and output data being these vector spaces. And in fact, we need to consider this very specific class of linear. So the normal maps between vector spaces are linear maps, but we actually need to consider these reversible unitary maps. And yeah, I've written here that U being unitary means that its inverse is its adjoint. And yeah, it's not going to be too important to understand this bit, but that's the sort of setting for the type of things we're really trying to describe in this talk. And so the key question we get to is, can we use any of the sort of programming language constructions that so on the classical side of that picture, we know lots of different programming techniques we can use. There's been years of like trying to work out how to do things. And can we use any of these for describing these unitary maps? So this is what we want. We want some sort of way to neatly describe the pure quantum computations that we're going to use all the time in quantum computing. And so, yeah, this is the sort of the key question that we're asking in this talk. And so what's like the current answer in a way? Well, basically, I think if you asked most people how they would describe a unitary map such that it can be sort of run on a quantum computer, they're probably going to say, well, I'm going to need to write a circuit for it. Is there a question? No. Okay, I'll continue.
I'll mute.
So yeah, this is sort of overall the most, yeah, I think if you ask nearly everyone who works in quantum computing, how do you represent a pure quantum computation, they're going to give you something like this. And just in case anyone hasn't sort of seen these quantum circuit diagrams, each of the different lines or wires is representing a different qubit. And then we have a bunch of symbols, and each of these symbols sort of represents some primitive gate that our computer knows how to run. And then also key is that we can compose these symbols together in sequence, meaning we do run one then the other, or we can run them in parallel. Like, yeah, can you see my mouse, by the way? Just okay. So we can also run them in parallel at the same time. And so that's sort of all we actually need to build up these quantum circuits. We have some primitive gates, and we're allowed to compose them in different ways. Oh, and yeah, so the question, the sort of being able to do this composition in sequence and parallel is great. We get a lot of structure, or we know a lot of structure of our quantum computation by knowing how it's composed together. This sort of very static structure allows us to do things like qubit routing and stuff like that, and like thinking about all our scheduling. So this part of the quantum circuit diagram is great. It's great that we can line things up and we can put them in parallel and know when that's happening. The bit that's maybe I'm going to try and convince you is not so great is all the different primitive gates that we have here. So what is going on with these primitive gates? Well, each gate is effectively some sort of, in a way, it's a black box. So each of these gates is given by some matrix. So all our linear maps, all our unitary maps can be described by these matrices. But other than sort of looking at this grid of numbers, we don't really have any way to sort of reason more about what's going on. So we can't like break this X gate down into more fundamental operations, or it's probably not, for some of the other like gates, it's probably not immediately obvious what these unitaries do. It's definitely not obvious what they do when you combine them together. I would be very surprised if anyone knew from the previous slide what that circuit was doing, unless they'd happened to see it already. I certainly would not have been able to generate that. And yeah, this is the sort of questions we're really trying to sort of solve with programming languages. We want representations of stuff where hopefully it's a maybe we've not made it easy to understand what's going on in a quantum computation, but hopefully it's easier than just seeing a big block of random gates spewed everywhere. And so, yeah, the claim sort of we're trying to make, or the claim that we're sort of basing this work on, is that these quantum gates really sort of sit at this awkward level in that they're not very easy to understand. Like, we can't look at these programs and really understand what's going on, but also they're not actually what the hardware is doing either. So they're at this awkward level of abstraction where they're not sort of high level for us to easily write programs about. I think if you look at any algorithms paper, they will not start drawing out circuit diagrams. They'll describe their unitaries using, they'll start just writing maths to like start building up stuff and describing stuff. But also, if you go right to the other way of like actually compiling stuff to a real hardware, you start having to go either have to pick some specific gate sets that they can support, so you'll end up actually having to transpile whatever you programmed into something else, or even going even lower level, all the gates get compiled away to sort of a sequence of lasers and stuff. So yeah, in a way, these gates aren't really what a quantum computer's doing. They're not easy to reason about, and so they kind of just exist as the best we've sort of got to try and describe these computations in a way that we know how to compile them down without knowing too many details. So yeah, the question is, can we do better than this? And our answer is, well, I hope to convince you that we can do slightly better than this. And we're going to generate this language, and the whole, maybe given away by the title of the talk, but the whole point of this language is that really the main component we need is this phase unitary. And so this is actually I would definitely view it as sort of the simplest unitary map. And it looks like this. So we take in, remembering our unitary maps are these maps from a vector space to itself. And we're taking in some input vector v, and all we do is we multiply it by some scalar. And of course, to keep this sort of unit vector condition satisfied, this scalar must be of, so it must be a complex number of magnitude 1, which we can write as e to the I theta. So I've got this diagram here. So basically, all our magnitude 1 complex numbers lie on this circle, and we can describe them by how far you have to go around the circle to get to that number. And so each of these things is a unitary map. And so in our sort of language we're generating, we want some way to represent this map, and we're going to just introduce some term constructor phase. So yeah, I should say we're calling each of these unitary maps a phase, which is, I think, quite standard. And we're going to write it in this form. So this term here is going to correspond to this unitary map. And then the idea is that we can actually build a full language using just this map. So this phase operator here, just this, and our sort of new quantum pattern matching construction, which I'm going to introduce in the following slides. So yeah, that's sort of the that's the story behind the title, at least, is that in a way, all you need, if you maybe squint a bit and ignore this line, all you sort of needed is this phase. And I hope, yeah, hopefully it will become more obvious how this sort of works. So I'll just, no one sort of butted in any questions, but I will continue. So the thing I need to describe is this pattern matching construction, because at the moment, all I'm able to do is multiply things by complex numbers. So let's sort of take a step back and think about what pattern matching looks like on this sort of classical computing side. I'm hoping most people have sort of used some programming language that has either like a switch statement or actually has sort of a pattern matching statement. But in general, when you've got some classical data and you want to do something with it, a very sort of natural thing you can do is sort of case split on this data. So if you think of this as a classical bit, a very natural program to write is that, well, we can case split or match on this classical bit, And when we get false, so when it's in the false case, we're going to run this program. And when it's in the true case, we're going to run this other program. And this is sort of a very natural way to split on this classical data. But of course, this classical data, I said it only sort of has two discrete values it can take. So how are we going to manage this for our quantum data that has infinitely many different possible values? And well, what we're going to realize is that to define a linear map, so all our unitary maps, we're trying to define a linear maps, we only need to, so to define one of these maps, it's sufficient to only define it on a basis. So I haven't really explained what bases are, but they're a collection of, it's a finite or a set of elements of our vector space from which we can generate all the others by sort of adding and scaling them in a unique way. And in particular, this ket0 and this ket1, ket0 and ket1 states that I introduced before form a basis for this this C2 vector space. And so what I'm doing here is I'm saying, well, X can be any sort of qubit state, but to tell you what I need to tell you what this program does, all I have to do is tell you what the program does when this qubit X was in the ket0 state, and what this program does when the qubit X was in the ket1 state. And you can actually tell what the program should do in all the other states just by sort of taking, just by sort of extending linearly. So sort of combining what these two programs do by adding them together and scaling them appropriately. So hopefully that sort of makes some sense of how this corresponds to this classical case. So yeah, the idea is effectively we're saying we've got some input qubit, and now if it's in this state, do this. If it's in this state, do this instead. And I'm telling you that's all actually you need to know what this program does on any state. And actually, this is already enough to define some of the gates that were on a few slides back. So if we look at, for example, the Z gate, the Z gate was given by this matrix. So maybe the matrix isn't the most easy way to see what it's doing, but what is important is that if we apply the Z gate to this ket0 state, it doesn't do anything. And if we apply the Z, so this, remembering this ket0 state was sort of the false state of our qubit. If we apply the Z gate to the ket1 state, we actually get minus ket1. So hopefully you can see that this sort of I've already described the Z gate in the way we need to write this program. So I'm trying to match on my input qubit Q, and so now I need to say what it does in the 0 state and what it does in this 1 state. Well, in the 0 state, we should do nothing, right? So if we're taking a 0, we want to return a 0, so we don't need to we don't need to sort of do anything if we're in the 0 state. And in the 1 state, well, we wanted to take in 1 and we want to output this minus ket1. And so what's happening here? What we're doing is we're multiplying by -1. And this is actually the phase map that we've seen already. So taking this ket1 to a minus ket1 is just this phase of pi, which if we actually sort of compute it out, we get that this is exactly multiplying by -1. So hopefully it sort of makes sense that this will definitely satisfy these two equations. If I pass in sort of a ket0 for this Q, nothing will happen. If I pass in this ket1, it will get negated. And then the whole idea of this matching construction is that, well, that was enough to describe what the Z gate does fully. So for any other input, we can just take the appropriate combination, much in the same way as the sort of matrix is doing. So the matrix is almost saying, I'm describing this linear map purely by what it does to these basis states. Okay. And then what we realize next is that actually, in the case we just saw, this match statement was kind of very verbose and possibly a bit unnecessary because we actually only wanted to do something on one of the branches. So what we've done here is that we want to sort of simplify this a bit and make it a bit nicer to work with. And we're going to borrow a construction from Rust, which is this if-let construction. So this is yeah, basically directly ripped out. Whenever you have a match statement like this, where one of the sides you're doing something and the other side you're doing nothing, there's this construction called this if-let construction in Rust. And basically you just write the side but you want to do something, and it's implicitly understood that the side you didn't want to do anything will be the sort of empty program. And so this immediately lets us write, firstly the Z gate, but also these other two gates, the S and T gate, in this sort of reduced if-let style. So if we read this top line, we're saying if our input qubit was of ket1, then we're going to do this phase multiplication. And it's implicitly saying that if it was in the 0 state, we wouldn't do anything. And there's another sort of nice benefit of this, that if we were to sort of use these, so I guess there's two nice things. Firstly is that if we really did want to use the full power of this match statement, we could still sort of do this with this if-lets. We just have to match on each part individually. And then, so if we really wanted to do something on the 0 state and the 1 state, we could sort of do if-let is in the 0 state, I'm going to do my first thing. And then we could compose this with the function that's saying, if-let is in the 1 state, I'm going to do something else. And the second nice thing is we now sort of lose this obligation of the match statement of showing that our cases are disjoint. So usually when we think about these sort of pattern matching things, we have to show that each of our cases, or we don't necessarily have to, but it's sometimes nice to show that the cases of our match statement never like coincides. And in this sort of statement, in this sort of world, that would correspond to these basis states being orthogonal. And that's something that's generally quite hard to syntactically check. But in this setting where we've only got one thing we're working on, we sort of lose this obligation. So that's sort of another nice thing. But the main reason was just it's shortened the code a bit. It's made it a bit more, there's less sort of unnecessary syntax floating around. That was the primary motivation. But you might be thinking, so I've defined a sort of Z, S, and T gate. I know it's a sort of a few slides back by now, but these were all sort of diagonal matrices. So have I really done anything that interesting yet? In a way, these were sort of the simplest quantum gates we had. And sure, I've described them with this if-let and this phase, but maybe that's not too exciting. So let's think about a different gate. So for example, I'm going to show you how to do this X gate, which is sort of the corresponding quantum gate to the classical so not or bit flip gate. So this is the gate that sends this ket0 vector to ket1 and the ket1 vector to ket0. So you might be looking at this and thinking, well, surely you're stuck now. So there's nothing we can multiply this ket0 with to get a ket1. So there's no phase we can, it feels like there's no phase we can apply to 0 to get 1, and it feels like there's no phase we can apply from 1 to 0. But then what we need to notice is that, well, I told you that this ket0 and ket1 form a basis of this, this complex vector space, and that we could use this basis as our sort of way to pattern match over a quantum data type. But this 0 and 1 is not the only basis of our vector space. So actually this plus and minus that I showed you right at the start are also a basis of C2. And if we look at what X does on these states, we see that there's a lot of sort of like multiplying things out in the middle. But if you start with X of plus, you sort of figure out what had to happen. You actually just get the plus state back out. So it doesn't do anything to the plus state. And if you apply X to this ket minus state, you sort of just follow all the rules of linearity. You again work it all through, and it actually turns out that you end up with minus of the ket minus state. So actually, it turns out this is exactly the same situation as we had before with the Z gate. We've got a basis of this ket plus and ket minus. One of them is left completely untouched by the gate, and the other is negated by the gate. So all we actually need to add here to be able to do this is a new one of these patterns to match on. So this X gate becomes, if our input qubit is in this ket minus state, then I'm going to negate it. And this actually, this is sort of almost the point that started this whole project, because I was very surprised when I first saw this sort of way to define an X gate. So I'd always thought of the X gate as the thing that sort of swaps the basis states. But there's this equally valid way of writing it where we're saying, actually what it's doing is it's negating this state instead. And in a way, this, I guess another interesting thing about this, to me at least, is that this feels like a very quantum way to describe a very classical gate, which, I don't know, maybe that resonates with some people as well. But I was very surprised that this gate that is sort of a completely classical gate, so it has this very quantum-like description where we needed to know about this superpositioned state to construct it. So I think I'm doing okay on time. So I'm gonna do another example, which I didn't give in the conference talk. So let's think now about this Y gate. So this is given by this matrix, sort of following the pattern we had before. There are two basis states, so this ket L and ket R, which I've given the sort of equations for here. But the important thing is that we can again describe this Y gate as it leaves this ket L vector fixed, and it inverts this ket R vector. And so what do we want to do about this gate? Well, we could sort of just add these things as patterns again, but then we get into this sort of trap where it feels like every single time we want to define a new gate, we're going to have to add more syntax. So then have we really done any better than the sort of circuits we had before if we're just adding a new pattern for every primitive gate? But what we can also realize is that we can actually already obtain these vectors, because this ket L vector is precisely applying this S gate to the ket plus vector. So remember the S gate, we defined it a couple of slides back, but it was the, I should have put the definition of this here, but it was the thing that's left 0 unchanged, and it sent the ket 1 to I times ket 1. So it's sort of doing half of the Z gate. And so, yeah, this basis of this L and R vector, well, actually, they're already obtainable. We just need to apply S to a basis we already had. So what we're going to do is that to our sort of syntax of our language, we're going to add this construction as a pattern. So for any unitary I've already defined, so remembering that any sort of program in our language is a unitary, if I apply any unitary to any pattern, then I get another pattern. And for example, in this, I can define Y as, so I can take this ket minus, I can sort of compose it, I can bolt this S term onto it. So maybe I can actually just go back and show that. This S term was defined here. So this is just, you can think of just pasting that in. And then I sort of apply the same trick as before. So I'm saying if my Q was of the form S of ket minus, then I'm going to invert it. And I'm hoping that sort of these three examples have made at least some amount of sense. So yeah, this sort of gives us all the constructions we actually needed in our language. So I'm just going to sort of try and sum it up and go over what our language actually consists of. So there's sort of two, so the two constructions being this phase operator and this if-let construction allow us to form a completely universal quantum language. And it has two classes of constructions. So the terms of our language, or programs, all represent linear unitary maps. So we have the phase operator here, which was the first thing I introduced. I should say that this is for sort of all angles theta. We have the if-let construction here. So we're saying if our Q is of fits some pattern P, then we will we can sort of run some program on the smaller part of, this is the program we're going to run when Q matches this P. And then we're also, this is right back at the start, but I said we had no problems with the sort of compositional structure of circuits. So we're going to keep this sort of running things in sequence, which is I'm going to write as S semicolon T, and also this running things in parallel with this tensor product symbol here. So we're happy to keep both of these, but then we've replaced all the sort of primitive gates by saying we only have this sort of one primitive phase, and we have this construction for sort of choosing a subspace to apply that phase to. And then the sort of unexplained part of this picture is what this P is, and this P is going to be patterns. So these, you can think of these patterns as sort of representing, so instead of representing unitary maps, they're representing these isometries of which state, like particular states are a subclass of. And yeah, these really allow us to sort of pick out a subspace of our quantum data, which we're going to apply some subprogram to. So we've got the 4 sort of basis states that we saw before. We've got this 0, 0, 1 pair of basis states, this plus minus pair of basis states. And then also we had this construction here on the which you use to make the Y gate. So this S can range over any of the terms in that were our unitaries. This P can range over any of the patterns here. And then we're also allowing, so I guess I haven't used these as examples yet, but we're also allowing to tensor product patterns together and also to have variables in our patterns. So this is quite usual if you're used to sort of languages that have pattern matching in. We can often have some pattern, and that pattern has a variable somewhere inside it, and that will sort of get instantiated when we match on the pattern. And there will be an example using that, so I should be able to show that in practice. But yeah, even without that, we're able to sort of define a completely universal gate set. Yeah, so from just those constructions, we can derive a universal gate set. We're hoping it gives some more intuition about what these things do, or at least you're able to sort of take your primitive gates and break them down into more fundamental constructions. So yeah, going to write the sort of very overview slide, I gave you this program, and I'm hoping now that we can at least, or maybe with a guided explanation, we'll be able to work out what this program is doing. So if we look at, let's look at first the inner bit. So we have this, we've got this qubit B, and we're saying if it's of this ket minus type, then I'm going to invert it. And so if we remember back, this inner part is directly applying an X gate to this qubit B. And now if we look at the outer part, it's saying, well, if we've got this qubit A and A was in the ket 1 state, then we're going to apply an X gate. And hopefully it's at least believable that this is going to give us our CX gate. So if we, so this controlled X gate where we effectively apply an X gate to the second qubit if the first qubit was in the 1 state. And we do, of course, we do nothing if the first qubit was in the 0 state. Are there any questions at this point? I think yeah, I've got a few more slides to go through of sort of cool things we can do with the language, but that's sort of the explanation of everything that's going on. So if there are questions, this would be a good time.
Okay, I have one question. How do you know that the phase pi is on B?
What do you mean?
Because you're only applying the phase on one of the qubits, right?
So we're applying this phase whenever A is in the 1 state and B is in the minus state.
To the entire system.
So each of these if-let expressions sort of picks some subspace of your system. So you can think of this outer one as picking the subspace where your first qubit is in the ket 1 state. And you can think of this inner one as picking the subspace where the second qubit is in this ket minus state. And then this phase is it is sort of, in some sense, a global phase operator, but because we've already specialized to some subspace, we are applying this phase specifically when A is in the 1 state and B is in the ket minus state.
Okay.
And so I don't think of it as applying the phase to B. It's that we have split this CX gate into ways to choose a subspace and then apply a global phase. And of course, once you've chosen a subspace, your global phase is no longer global, and it now becomes, well,
Right.
something that's actually computationally relevant. So
Got it.
yeah,
Okay.
I think, thanks for the question. That's yes, I think it's, yeah. I think the main answer is I don't view this phase as applying necessarily to B. It's applying to the subspace that is determined by these patterns. Okay.
There is a question in the
So,
chat. I don't know if you saw that.
okay, I did not see that. So the question was, how do you define time dependence in your language? On one slide, you have the T gate as being equivalent to the phase. So, right, so at the sort of start of the talk, we sort of talked about this quantum circuit representation being not particularly close to the hardware representation and not particularly sort of human manipulatable either. The aim of this language is not so much on the being close to the hardware side. This is definitely on the trying to be more human understandable side, or having more ways to reason about these things. So yeah, just because the T gate has a sort of very simple, just because it has a very simple term does not necessarily mean that implementing it would be straightforward. I think, I don't know if that answers the question properly, but yeah, I think the answer to this, that the first bit of how do we define time dependence, we're not nothing is sort of specifying how long any of these gates will take to run. So that's at a lower level of compilation than we're considering here. Okay. So yeah, once we've sort of broken down all these primitives into this phase language, there's actually some interesting things we can do with it. But there's some interesting things we can do once we've done this. So the first is that we can I sort of told you right at the start that these unitaries are these invertible maps, and we can actually sort of syntactically define this inverse. So we can sort of just go through all the constructions we have, and we say, well, if I want to, for example, if I want to invert doing S then T, then I do the inverse of T composed of the inverse of S. And then all I actually really needed to sort of know is that to invert one of these phase operations, all I had to do is negate the angle. So if you think back to the quantum circuits, if I wanted to invert a quantum circuit, I would need to know how to invert all the gates in my circuit. So I probably have to be just told that ahead of time, like what the inverse of each of my gates is, or if you are making some system to do this automatically, you would need to tell it all the sort of pairings of gates and their inverses. But here, all I really needed to know is that I've actually got this one sort of primitive phase gate, and this is how I invert it. And then the nice thing is that to invert one of these if-lets, well, if we think about it, it was sort of focusing on some subspace and then applying a term. So all I need to do is, to invert that, is focus on the same subspace and then apply the sort of inverse term. So I don't have to worry about these patterns at all. I just need to invert this whole term. I just focus in on the inner body, and sort of I didn't have to change anything about the pattern, which was sort of nice. So really, the only thing I needed to know was this. And then perhaps a bit more exotic is that in addition to sort of doing inverses, we can actually define, if you knew your term didn't have any of these semicolons in, we can actually sort of exponentiate it to any real number. So for example, you can take a gate that's defined as a single phase and take its square root, for example. And to do this, we sort of do the similar trick of, well, the tensor things just go inside. The if-let expression, again, we just move the sort of move this exponentiation operation into the middle. Of course, we cannot do the case for these compositions, which is why we're sort of saying only the composition-free terms are exponentiable. And and then once we get down to the phase operator, well, we just need to, if we remember that this phase operator is sort of yeah, this theta already appears as an exponent. And if we think about sort of our laws of exponentiation and calculate out a few things, we can see that, well, we should just multiply by this x we've got here. So for example, we can use this to sort of, we defined, earlier we defined this S gate as saying, well, if it was, we did this if let of one, of ket one, and then we applied this phase of half pi. But what we could have actually said is, let's just define S as the square root of Z, for example. And so, yeah, I'm not sure how widely sort of useful this is, but it was at least sort of interesting to me that you could actually take any of these gates that you'd managed to define as a single phase and then take their square root or take them to actually any power you wanted. And I should say that these aren't like extra. So I'm calling these meta operations. These aren't. I'm not adding more syntax to the language. I'm just saying, if you've got some term, you can actually sort of macro expand out what its inverse should be or what its exponentiation should be to get another term. So we're not sort of adding anything to the language. These are just operations on the language. So another thing that we can do, which is kind of we add to sort of show that we're not, I guess we're not sort of doing something that's just completely meaningless and not runnable at all, is that for any of our terms, we can actually sort of recover some circuit from it. I'm not necessarily claiming that what we've got here is the most efficient circuit compilation or most definitely the way you'd want to do this, but it's more of a proof of concept that it definitely is possible. So in the paper, there's a much more sort of rigorous way of how to compile any of our terms down to a circuit, but I thought I'd just go over the interesting cases in this slide. So whenever we sort of have this scenario here where we've got what we saw earlier, we match on this ket1 state and apply some phase. This always corresponds to some sort of RZ gate with the angle theta put in. And then also we saw this earlier with the C0 gate, but if we've got some, again, this sort of if let ket1, but then we've got some bigger term on the inside, this sort of turns into this controlled version of whatever gate S did. And then maybe less obviously that if we are matching on sort of this ket minus state, we might think, well, how are we going to sort of think about what that's doing? Well, what we can do is we can realize that ket minus was actually the Hadamard applied to ket1. And by conjugating in the right way, we can still sort of see this as a controlled gate. So in a way, this sort of if let ket minus is a generalized control. So I think probably people are familiar with this this sort of black dot control, which is controlling on one. I expect a lot of people will also see in sort of the version where you have a white dot to mean zero controlling. In a way, this is sort of extending 1 and 0 controlling to being able to do plus and minus controlling. And then lastly, whenever we have this sort of term applied to pattern going on here, where we had some unitary T and some pattern P, we can actually always compile this out into sort of a conjugation. So I'll try and sort of explain what this means, but so this will compile out into first do the inverse of T. So this is using this sort of inverse meta operation that we defined. Then do the thing without this T dot, and then finally do T. And we can sort of see why this works. So if we imagine Q was in the state T applied to P, well, once it goes through the inverse of T, it will be in the sort of state determined by P. Then we apply the middle of the gate body, and then we put it back to being in the sort of state it was meant to be in. I think it's fine if this doesn't immediately make sense, but the point is that even if we've got some sort of arbitrarily complicated pattern here, we can still sort of compile out what the circuit should do. And yeah, again, I'll stress that this is not necessarily the sort of most efficient way we could compile this, and it's definitely some sort of future questions of can we sort of compile these things well into different gate sets and have this as sort of a gate set agnostic representation of these programs, but that's not something we really tried to tackle in this work. In this work, we just wanted to show that we sort of hadn't done anything that was obviously not computable in any way. And then I think I've just got, okay, oh yeah, I got an example of this Y gate. So if we remember this Y gate fitted this sort of pattern where we had we applied this S to the ket minus, we matched on that and then applied this. We can sort of follow out the rules I put in the previous slides. So this is equivalent to doing the inverse of S, then this thing in the middle, and then the S gate. And then I told you that doing this sort of this ket minus matching was the same as doing a ket. Well, maybe I didn't actually explicitly write this, but it's the same as doing this ket one matching surrounded by Hadamards. And then once we sort of further gone down and worked out what these things mean, we get that this is equal to this circuit. If you then took the output of that and ran it through your favorite sort of circuit optimizer, you'll probably realize that this Hadamard Z Hadamard is an X gate, and maybe you would even realize that this is sort of the standard, or if this is a standard representation of this Y gate. I guess this is the circuit representation of a Y gate using S and Z X gates. So like assuming you didn't have Y gates. So yeah, just to sort of show how this gate that has, we've used all these fancy constructions, but we can still sort of reduce it down to a more usual gate thing, which they could then, of course, be further passed on to your actual hardware. And then I think I've got time just for one more interesting example, or an example that's interesting to me, which is this swap gate. So this swap gate commonly has this circuit representation. And to me, at least, it's completely not obvious why this circuit would swap the two qubits that you inputted. But we can ask the question of, well, can we sort of play this sort of compilation procedure backwards and determine what this term could have been? And yeah, we sort of can. So we can immediately see that, well, this is 3 CX gates, obviously. But then if we remember back a bit, when we have this sort of, I might have messed up the notation here, but we're in this situation where we're doing this sort of conjugation. So if we think about the CX gate is inverse to itself. So what we're effectively doing is an inverse of a CX, then we're applying something in the middle, and then finally applying a CX. And so this fits into sort of this if-let of a unitary applied to something. This is actually the only place I've used this pattern variable. If this doesn't make sense, that's fine, because I've definitely skipped out a few steps on the way to being able to define this. But hopefully it makes some sense that, well, this is the same as doing this. We're sort of wrapping this CX in an if-let, and then we're doing a CX the other way around in the middle. We can expand that all out to get this much longer expression. So all I've done here is I've replaced this CX by its definition. And then one of the sort of laws we have for our language is that, so this is something we've proved always holds, is that whenever you sort of have these nested if-let expressions, you can sort of push them back together. And the way it pushes back together in this case is that you can actually define the swap gate as this last line. So it's saying, yeah, if-let, we've got if, so the pattern with, sorry, I should have used dots instead of brackets as I've used elsewhere, but imagine there's sort of a dot between this CX and the state here. We're saying if our input matches, CX applied to this minus and 1, then we're going to invert it. And that might not make much sense, but actually, if we sit down and calculate what this is, if we sort of write down everything, even though it's not in our language, we end up with the, I've written the inverted commas because this is not a term of our language, but this thing here, if we if we mathematically calculate what it should be, it's a scalar multiple of this state here. So it's the 0, 1 state minus the 1, 0 state. And so this actually gives us a second way to think about this swap gate, is what it's doing is it's taking this state here and inverting it. And so it's multiplying it by 1, minus 1. And what that does is it effectively, very directly swaps these two states. So it's taking the state where we had a 0 in the first qubit and a 1 in the second qubit, and swapping it the state where we had a 1 in the first qubit and a 0 in the second qubit. yeah, again, apologies if that didn't make much sense because I think I rushed through it a bit too quickly. But the sort of idea, if you get a chance to think about it a bit more slowly, is that we really sort of get a second way to understand this otherwise quite opaque swap gate. And then, yeah, that's sort of where I'm going to end. So that was sort of a sort of quick explanation to what our sort of programming language is, or like I guess more of a prototype programming language, but it's got a quick explanation for what this is doing. In the paper, we went sort of a lot further with proving stuff. So we defined actually a type system for everything and gave it some semantics. We fully defined this evaluation to circuits. Some of the sort of these equalities I talked about with the sort of on the previous slide saying we know that these two programs are equal. We proved some of these in our semantics. And then we also sort of took some of the sort of classic, the well-known quantum algorithms and tried to see how they would look like in our language. In the future, we'd love to work on some of these things. So it would be really interesting to see how measurement fits into this picture. Given that we already have sort of a way to represent bases, it feels like it's a natural extension to say, what if I measure into this basis? But of course, this introduces some more questions of what we need to sort of add more classical types alongside our quantum types and have things playing nicely. So that's not something we got around to doing. We'd love to sort of extend these equalities to a full-on equational theory. And it might be interesting to sort of look at operational semantics instead of these categorical semantics. And finally, I sort of have the intuition that this might be a good sort of playground for doing optimizations on. It's a sort of common theme that when you've got, more high-level constructions, you can often do optimizations that weren't apparent before. But again, that's not something we've looked into. And then I'm lastly going to sort of advertise that I wrote sort of a small implementation for a slightly more basic version of this language. And yeah, you can have a play around with it and write some terms, pass them and type check them and like see what unitary matrix you get from the end of it. And yeah, that's all I've got to say for today. So I hope that was understandable and I hope people enjoyed it.
Cool, it was.
Lots of questions. Alex, yeah, you feel free to call out names in whatever order.
I was going to start with the chat, given that I saw that first. So yeah, the question of does this have error correction in mind? We did not explicitly have error correction in mind, primarily because so in my head to talk about error correction, you'd need some way to talk about measurement and hybrid things going on. So this is definitely something we could think about in the future. It could be sort of interesting to say, can I represent my sort of stabilizer? Like, can I represent my different stabilizers as patterns and somehow measure them out? That's definitely something that we could think about. But yeah, I think we'd need a good story for measurement before we could think about that. And so that wasn't so much what we were thinking about here. Sorry, I didn't read the second part of the question. Right. I'm not sure I understand the second part of the question, but if you want to elaborate on that in the chat, feel free. Yeah, this is not something we had in mind, but I don't think it's. I don't think anything we've done is sort of conflicting with error correction, but and it would be interesting to think about in the future. Do you want to call out people and to give questions, or should I just pick people?
Yeah, go with whatever order. I don't know that we get that.
Okay, I'm going to go with the order that people appear on my screen. So sorry if this is not the order you put your hands up in, but Timon.
All right, I think I managed to unmute myself. Sorry.
Yes.
Yeah. Yeah. So I mean, I'm one of the authors of Silk, and Silk is naturally based on isometries. And I've definitely missed this kind of feature in our language because whenever we needed to kind of conjugate by an isometry, we actually had to re-implement the whole operator as a unitary one. So I think this is definitely something that probably most high-level languages should have.
I think this is something I sort of forgot to mention, but we're not almost viewing this as sort of a fully, like, I don't think this, what I've described here, is like the full language you'd want to work with. I really sort of view this as, here's a sort of nice primitive that could be added into current languages that also operate, like, so obviously like Silk's doing all the young computation stuff, and I sort of view that as orthogonal to choose, like, having a nice way to describe your primitive gates in a way. I don't know if that makes sense. But
yeah, absolutely. I mean, that's expected for a Popper paper, I guess. So
yeah, we tackled one part we were doing, and the main point I wanted to get across is that I view these features as not separate from other features that have been. So yeah, other languages have obviously extended the circuit model in other ways, and we don't view these as conflicting. It's
me neither. I mean, we will probably as soon as possible adopt something like this. So one question I had, I think in the paper you said that Unity has exponential blow up in its compilation, and
we believe that to be true. I'm not an expert on
Unity. I also believe it's true. So one thing is for the sort of quantum if statements that are in Silk that are only like constrained to being in the set basis, we were able to get rid of this exponential overhead. But I think what you're doing still actually has exponential overhead, at least in the suggested compilation. And I was just wondering whether you see any realistic way that the compilation of this will not just blow up in general.
So I guess there's two ways that the compilation can blow up. So the first way is if you have sort of a multi-controlled gate. So obviously you can very easily write a multi-controlled gate in this. If you wanted to compile that down to 2-qubit gates, then you will end up with probably, I think that's an exponential, or is that just a quadratic? I can't remember, but that will increase the size a lot. So that's sort of unavoidable. So, and then the other place that I see the exponential growth coming in is with this rule. So we sort of taken here that if you've got this T, we've sort of replicated it twice. And if you imagine that T was some sort of deep stack, then doing this conjugation would multiply it. What we sort of tried to prove in the paper is that actually going from our language to circuits with multi-controls and conjugation is linear, and then compiling out the conjugation would be exponential, if that makes sense. So I don't think anything's too... The only sort of bad thing is this operation, and this is as bad as having sort of a conjugation operation. And it's only exponential in the sort of depth of T, which is often quite low. So I at least didn't know of any other exponential blowups that we had. It was definitely an aim of sort in comparison to what came before, we were really trying to not have a massive blow up when you compile to circuits. And I think this having conjugation is the only really offending one.
Yeah,
but
I mean,
if you have conjugation, then you can do an exponential blow up. So that's sort of unavoidable.
Yeah, well, I mean, it is avoidable if you constrain yourself to being in the computational basis. We have done that, and so I was just wondering, are there any other cases you have thought about?
Oh, I see. So you're saying if you don't... what I'm saying is if you have a sort of a conjugation operation as part of your language, then that naturally lets you have an exponential blow up because you can nest these conjugation operations inside each other. And that will...
Yeah, I agree.
So I don't think, for example, this has an exponential blow up, the ket minus. I don't think that's any worse than the ket one control.
Yeah,
we just need to conjugate with some Hadamard's. So yeah, maybe we can, I don't know if that answered the question. I don't think there's any horrific
I just think it's interesting to see how far it can be pushed, because there are cases where we can avoid it. And basically one interesting question is when what are other cases where we may be able to avoid it?
Okay. Thanks for the question. I think Jay's next on my screen, whoever Jay is. Hello?
I'm you. So I love it. I really like all attempts to represent things in a different way to how they are represented. It helps to reason about things. Now, in the response to, I think, Purva's question earlier, you said that this is more towards the human side of things, to like make humans understand better. So the question that popped in my mind at that point is which humans? Because I mean, I've never seen a language that all humans can understand better. So we're talking here of physicists, mathematicians, scholars, philosophers. In line with that, you are at a university that's full of people. So have you done focus group with different types of people to see if some of them find it easier or harder to understand?
This is definitely not something we've done. I'm sure it'd be interesting. It's just something I have absolutely no expertise in at all, in sort of actually trying to quantify how easy something is to reason about. I am definitely, when I said for humans to reason about, what by humans I guess I mean people that want to write quantum algorithms or want to write quantum computations in a way that they are runnable. So yeah, anyone who's currently writing quantum circuits, that's who I am targeting.
Oh,
I have no claims of whether I've actually made anything easier for them, but yeah, I think there was already some nice sort of reasoning steps we could do, like the doing the meta operations that were definitely sort of needed a more involved, or at least you needed a sort of case split on all your primitive gates. I think there's a good case that we've definitely not made anything, or there's a good case that we've not made things worse because we can still sort of define all the quantum gates you had before. And if you really wanted to use them as black boxes, you can, and nothing's wrong with that. So yeah, I have no hard evidence that this is easier to reason about, other than it sort of made sense to us, and we hope it makes sense to other people. I don't know if that's maybe a poor answer, but yeah,
no,
we don't have an answer.
That's a very good answer. As somebody who deals with circuits, the follow-up question that I would have is, I would love to know how far you can get a single abstraction into multiple operations. Because I mean, on these very small ones, it seems very comparable to just writing a circuit with different symbols. But if you can use one of those things, if, let, whatever, be this for 10
so
operations.
I think the nice example that we have in the paper is this Grover diffusion operator, which you can write as one big if-let. So that's like if-let, a load of plus states, do a phase. And so, yeah, there's a couple of other examples in the paper. I think that's possibly the most appealing one from like actual algorithm side of something that would usually need quite a few different gates. And obviously we're sort of cheating by putting a massive multi-controlled gate in the middle, but it kind of is what it is. Okay, thank you. I think Brian was next on my.
Thank you very much for the talk. So one of the things that looked interesting, especially, was like the dagger and how you can easily do that by just negating or changing the sign of the phase or the thetas in there. And I can see how that is kind of faster and easier and an optimized thing. And I was wondering what other kind of pieces of the language are similar where they have that kind of optimization, or even just an easier way of thinking about it.
So I guess the sort of key idea of the like one of the ideas you've got going on is that to understand a quantum circuit, you need to understand all the different gates that are in that quantum circuit. We're sort of claiming here that all you need to understand is this phase operator and how this if-let works. So I guess that's the sort of first reasoning thing that we've got fewer constructions, so you need to know how fewer things work. Mm-hmm. I personally like the exponentiation example. I think trying to work out yourself what like a square root of a x gate, for example, can be quite involved. Whereas here, well, it becomes very obvious. We just take our x gate and we take the angle in the x gate and we half it. I also like to believe that the sort of things we're writing here are slightly closer to the way that mathematicians would write unitary operations. So this sort of idea of splitting on bases and deciding what to do on each basis, I think you can. Yeah, I guess I haven't really done this sort of case study on to tell when this is really making things easier, but my intuition is this is closer to the way mathematicians write unitaries. And so, yeah, there was, I guess the only other point I have is that there are a couple of other sort of equations that hold between terms that hold in our sort of theory. And I don't know, yeah. I think there's a bit more in the paper to say. That. I don't know if that helps answer. Sorry, I'm sort of just rambling for every question.
No, that was great. Thank you.
I think Timon's got his hand up again. Is that the last one, possibly? I don't know if I need to. I guess people can leave whenever they want, right?
But I think this could be last call, last question.
Yeah, basically, it's just one comment about the intuitive thing. I mean, that's obviously something we have faced with Silk as well. And I think one thing that has become easier to evaluate here in terms of how easy is it to understand is that now we can kind of try to use LLMs and then see what strips them up. And then that is often a good proxy where you don't need to do this sort of huge studies with like hundreds of people. And the other thing is another question that I had, but I didn't want to add it because it was going on for a long time already at the beginning. Have you thought about adding things like else to this, like doing something to the orthogonal subspace?
So yeah, I tried to briefly say it way back. I guess where was I? Here, so there's two things. So if you have the composition, you can already write the doing something to the orthogonal subspaces, do it to the first subspace, compose with, do the other thing to the second subspace. We could think about adding a more general match thing. The downside is that you now open yourself up to this question of showing that my match branches are orthogonal, and this maybe gets difficult when you have sort of unitaries applied to patterns and stuff. There are in the literature, there are various syntactic checks you can do. So this is something we could do, but we didn't see it as necessary. And we thought the system was simpler just having the one-sided match. You could do it the other way. But I guess the other motivation for us is that nearly every example we came across was of this form of do something to one of the sides. So like most of the primitive gates that at least you find in sort of I guess there's no standard gate set, but a lot of the gates appear in this form. A lot of the algorithms seem to be of this form too. So that's what we ended up sticking with.
Yeah, makes sense. I guess a related point here is that you're kind of doing the commutativity checking in the standard computational basis.
Doing the what checking, sorry? The orthogonality.
Not the commutativity. I mean, you're not doing orthogonality checking. You're kind of, you don't have to because you're only handling one thing at a time. But if you have two nested if statements, then I guess in general, you could do this whenever you have some sort of commutativity constraints, which is probably also related to what you would do with measurements.
And I guess if you wanted to tell if two things commute past each other, then you would need to know if the things, they were acting on different subspaces, right?
Yeah, and I think, I mean, you can commute now, right? And this is because you both if statements, they operate on like separate variables. I guess you have some linear typing going on there, where the variable cannot be used again, right?
So the actual language that we proved loads of stuff about in the paper was sort of this reduced combinator version. But if you wanted to implement the sort of thing that I've written in the slides, you would definitely need some sort of linear typing going on to make sure that you're not duplicate matching on the same variable.
Exactly, and I think that is kind of a way you're constraining yourself to the set space is in a similar way that Silk does in general for if statements.
Okay. Yeah, we have, as I sort of put in the last slide, we haven't thought too much about all the sort of equations that can, certainly, yeah, haven't thought about all the optimizations and equations, but definitely something that would be interesting to look into in the future.
Well, thank you, Alex, and thanks for going along to answer all the good questions. Appreciate it. So yeah, everyone, if we just who's left, give a round of applause. Thank you so much, and yeah, appreciate.
Thanks all for listening.
Awesome.
Thank you. It was really good.
Thank you.
Take care, everybody.
Thank you.
Thanks, Alex.
Yeah, I'd be happy to answer more questions on Discord, I guess. If anyone comes up with anything later, I should be able to check it every so often and give an answer if I can.
Awesome.
Yeah, thank you.
And thanks to him. Yeah, thanks for inviting me to get to talk.
Yep, absolutely.
Good fun.
Take care. Bye.